Hello, class. I just realized something with the last couple recordings of yesterday and stuff is that what I have to do is each time I start a new video lecture, I have to go into the other camera software and change it. I'm not change it, but at least bring it up. Once I bring it up and I put it back down again, and I go into this, it comes up with those, with the manual and the brightness and everything else. But if I don't do that, then it reverts to whatever Zoom has in it, which is automatic focusing all the time and everything else. Well, it is very late for the lecture today. I do have some coffee here. And I am going to try to do this lecture. A lot of things have sort of jumped in the way. We had a department meeting and we're talking about a lot of things, dealing with fall semester and everything else. Yep. You guys aren't coming back in the fall, are you? I think you're done now, right? Who knows? But usually electromagnetic field theory is one of the last things that you have. I'm also trying out my new acetone tipped pens that I dipped in acetone yesterday. I better put the cap back on it. Because so anyway, and I have other pens too as backup, so don't worry, I have plenty of pens for the thing. All right, so what I want to do today is an example. I think the easiest way is to look at an example of coax and see how we use the various different equations and stuff for coax. And these, I did derive one of these equations for the capacitance per unit length in an earlier video, and I will refer you to that. But I'm just going to give you the equations for capacitance per unit length, inductance, conductance, and resistance. And then we're going to work through a problem and just look at what's happening. So what I want to do is I want to look at 75 ohm coax. Why do I say that? Because I mean, it could be 56 ohm, 85 ohm, 58 ohm. There's 50 ohm. There's a lot of standards. Did I say 50 ohm already? Who knows? But 75 ohm is very common to most people because 75 ohm coaxial cable is what goes in the back of their TV set, right? And everybody's familiar with the diameter of that cable. You're familiar with what's inside the cable. Chop a cable in half. If you're not, there's white, foamed polyethylene in between the inner conductor, the inner copper signal wire, and the outside braided aluminum ground shield on the outside. And of course, the great thing about coaxial cable is it carries its own Faraday shield, doesn't it? So it's a Faraday cage. So if there's outside interference, all that interference immediately hits the outside ground shield, which entirely surrounds the center signal wire. Let's just draw a coax here. I'm going to exaggerate, of course, the inner diameter, right? And I do that, and I can't really draw this. I'm going to draw this radius B. But the way that I'll draw this in here is I'll say that this is 2A, because the radius, the inner radius, is actually A. And I'll just say the diameter is 2A, and then you'll get the idea that the radius is A, right? So the radius of the ground shield is B, and the radius of the center conductor is A. You can look at that however you want to. Now, there's several different characteristics about this that you can find out. So when we look at the equations for a coaxial cable, the first thing that I want to look at is the equation for characteristic impedance for a coaxial cable. Now I'm going to use a new symbol here. I'm going to use, well, it actually looks more like that. I'm going to use the symbol eta, right, divided by 2 pi. And then that times the natural log of B over A, right? And that equals the characteristic impedance. Now, what is eta? Eta is actually the square root of the permeability over the square root of the permittivity of the dielectric, right? So of the dielectric. And in the case of a coaxial cable, in the center there, and I guess all I can use is blue because I haven't found that red pen yet, but there you go. You got all that stuff in between. Well, that's not good, is it? Because you can't even see through that and see the A or the B now. But whatever. So anyway, in the coaxial cable, that foamed polyethylene that's in there, the relative permittivity of that is 2.3. That's a 3.8. All right. I've got to find that red pen, or maybe some highlighters or something. So so that's it. What eta is, and using this equation. So now what I want to do is I want to look at a coaxial cable that has this characteristic impedance, 75 ohm characteristic impedance. And I'm going to say that the center radius is 1 millimeter. All right. So A is 1 millimeter for the coaxial cable, the center radius. Now, if we use this equation here, I think everybody can see. I don't know how many steps I've got to go through to actually do this, but let's just look at what we have here, so that we know that this is going to be, or this is going to be 75 ohms. So why don't I rearrange this a little bit here? Let me just put this, since this is really all by itself, two separate steps here. Let me put natural log of B over A on one side by itself, so that we can handle all of the algebra before we actually get to getting rid of that natural log. And so I've got 75 ohms. Where'd I get that? That is the characteristic impedance, right? And then I've got the, yeah, then I've got the, where am I? Oh, yeah, times 2 pi divided by eta. Okay, now let's solve for that all by itself. Let's just look at eta all by itself. What is it that we really have here? Right, the square root of mu divided by the square root of epsilon. Let's look back at the equation for a second. Let's look at the equation for a second. Now we know that the characteristic impedance is in ohms. It's 75 ohms, isn't it? How about this? What are the units for the natural log of a ratio? Well, I think everybody knows that there are no units associated with a ratio, and there's no units associated with the natural log of a ratio. How about 2 and pi? Those are two numbers, aren't they? Do they represent something here that I've got units for, or something like that? No. No, they don't. So we know that this is going to represent ohms, isn't it? In fact, why don't we look at a very special case of this? Because really, what we're looking at here with eta is really the square root of mu sub r times mu sub o divided by epsilon sub r times epsilon sub o, right? Does everyone see that? You know, can't I break that up? Couldn't I break that up and say that that is really the square root of mu sub o divided by epsilon sub o times the square root of mu sub r divided by epsilon sub r. You know, I'm also going to mention this. Mu sub r in everything that we're going to be doing in this course is going to be 1. Now, I want to point that out for several different types of materials. Where can I do it? I'll do it over here. So for gold, right, epsilon sub r for gold, is this a new? No, it's not. Epsilon sub r for gold is 0.99996. For copper, epsilon sub r is 0.99999. For aluminum, epsilon sub r is 1.00002. And for silver, epsilon sub r is equal, no, that's gold, isn't it? What is silver? So, I don't know. Silver, for, for silver, it is 0.99998. So you can see that everything here is literally 1. So all of our, you know, oh, did I say, oh my God, where is that markout pen? It's not epsilon sub r that I'm writing there. Oh God. First lecture of the day, and it's like 5 o'clock at night. So, yes, there will be mistakes. No, it's not epsilon sub r. It's mu sub r. Mu sub r. It's mu. I'm going to write it in there, even though it's going to ruin this pen. Mu sub r. Mu sub r for all of those is 1. For everything that we're going to be doing in this class, mu sub r is going to be 1. If it changes, I will let you know what it's going to be. But let's just say it's 1 for right now on everything that we're going to be doing. Now, let's get back to this. Now, so let's look at mu sub o over epsilon sub o. What is that really? So if I have that, that would be the square root of 4 pi times 10 to the minus 7 henries per meter divided by 8.85 times 10 to the minus 12 farads per meter, right? So, and then of course taken to the square root. And I think if everybody works that through, they're going to see that that comes out to 377 or 376.9, I think it is, ohms. Right? Does everyone see that? That's what that part is. Now, how about this part? Now, I said that the numerator is always going to be 1. So if the numerator is always 1, then epsilon sub r, oh, look at that, is 2.38. So we still have epsilon sub r there, don't we? So let's look at what this actually becomes, because we got 377 here and we've got epsilon sub r in the denominator. don't we? So let's I think I can finish it off here. Let's just see. So this would be 75 ohms. I'll write small times 2 pi. Right now, I should have the square root of epsilon sub r, right? That's left over. But then in the denominator where this is, that would be 377 ohms, right? Because can everybody see this right here would be 377 ohms times the square root of that, that'd be 1, divided by the square root of epsilon sub r. And that's all I've done here is I've just taken that and switched it around so that we can get the natural log of b over a. Now I should probably cut that part of the problem off so that everybody can see what I've done there. And then we'll go along with natural log of a over b here. And if I throw all of that in there, I should get 1.92. Let's see if that is sort of right. Let's see, that'd be 6 times 75. That'd be 450, so a little bit higher than the square root of 2.38 is like, what, 1.9, or I don't know. So yeah, that seems about right. I could turn this off and check on it, but I'm pretty sure that that's right. I've done it enough times. I'm just thinking I left something out there. I'm not thinking I left anything out here. So what this does is that says that B over A then, right? Because we know that e to the x is the inverse log, so e to the natural log x equals x, and the natural log of e to the x equals x, right? We all remember those identities. So that's all I've done here is I've taken e to this side, which leaves me with b over a, and I've got to take e to the other side, so I've got e to the 1.92. And that means that B over A, the ratio of the outer ground shield radius, and I say radius all the time. Now, even though you might think, oh, hey, well, the ratio of the radius to the radius of the outside to the radius of the inside would be the same as the ratio of the diameter to the outside to the diameter of the inside. Not, yes, that's true, but that is not what B or A are. B or A are the radii, and they come in to the solution of the resistance per unit length later in the problem. So we have to always remember that they're radii. It's not a ratio in one of the in one of the characteristics of the transmission, the resistance. And let's never forget what the communications circuit, looks like. This is it. Except the G prime is always 0. And then we've got L prime, we've got C prime, and we've got R prime. And those are all resistance per unit length, capacitance per unit length, inductance per unit length, and then, of course, conductance per unit length, which is 0. So we've got this, and then we take the e to the 1.92, and we get 6.82, right? And we know that the outer radius is 1, or the inner radius is 1 millimeter for the inside signal wire radius, right? Which means the diameter would be 2 millimeters. And so we've got an outside radius then of 6.82 millimeters, right? So we know that B equals 6.82 millimeters. There, that's good. So we know B equals 6.82 millimeters. We know A equals 1 millimeter. We know the ratio between those two is 6.82. And we also know that the natural log of B over A, because we're going to need that later on in the solution of some of the characteristics here is 1.92. So let's go on to the other characteristics. And we're going to start with inductance. Inductance per unit length is the permeability of the dielectric divided by 2 times pi times the natural log of B over A. I'm also going to give you the other ones as well. So capacitance per unit length is equal to, and I derived this in class in one of the earlier lectures, 2 pi epsilon divided by the natural log of B over A, right? And then when we look at R, and what R is for the thing, we have 2 things here, and I want to write them both down. So R prime is R sub S, and I haven't talked about that variable yet, but R sub S divided by 2 pi times 1 over A. And can you see now why we have to use radius? We have to make sure that's radius because there's no ratio here, is it? Plus 1 over B. That also says something about the resistance per unit length in a larger diameter cable as compared to a smaller diameter cable. And I'll talk about that later. I'm going to do a special example on that, showing you at the same frequency, a larger diameter cable would give us much better attenuation properties, much lower attenuation properties. So this is this. Now, the real question that you're probably having is, what is R sub S? Right, what's R sub S? R sub S, by the way, of all the various geometries that we're going to work with, the only equation that always is going to stay the same is R sub S. All right? Okay, so R sub S. And you'll have seen an equation similar to this, but entirely different in the skin depth equation that sort of looks like this, but the units are all, the variables are all arranged differently. So try not to get this confused with the skin depth equation, but maybe I'll put it up there anyway. Now, I like to write R sub S like this, right? R sub S pi F mu rho. And the mu here and the rho are the mu of the permeability of the conductor, and the rho is the resistivity of the conductor, right? That you've got in the middle there. So I'm just going to put sub C here because you're already familiar with that the C means conductor. Now, that equation looks similar to the skin depth equation, but it is not the skin depth equation. The skin depth equation, if you go back and refer to that in your notes, doesn't look anything like, well, it does look a lot like this, but it's not this, right? Because anyway, go back and look in your notes and you'll understand why. Now, let's go on, though. So if this is what we've got, and remember, you know, mu equals mu sub R times mu sub O, right? So all of these are like that. Now, when I'm talking about mu here, I'm talking about the dielectric. When I'm talking about epsilon here, I'm talking about the dielectric epsilon. All of those. But here, I'm actually talking about the conductor permeability and resistivity. All right. Well, let's do the first one first then. Why don't we do that? Because that's a very easy one, and it's just inductance per unit length. So when I do that, I just pop in 4 pi times 10 to the minus 7. Didn't I say relative permeability was always 1 in everything we're doing here? So I'm not even going to write the 1 down. Okay, I'm going to write the 1 down. Divided by 2 pi times the natural log of, you know, I'm going to put the natural log of b over a, but when I calculate it, you know that the natural log of b over a is just 1.92, right? So you can see what I'm doing there. And what that comes out to be, by the way, is 300, you're probably already ahead of me, 384 nano henries, that's a nano, henries per meter. All right, pretty straightforward. Let's do the second one. Now we know that there's a relative permittivity of the dielectric foam that is 2.38. 2.38, right? So we have to include that in there somehow. So I've got 2 pi, right, times 8.85 times 10 to the minus 12 farads per meter. Oh, I gave myself a haircut today, and I still have the same shirt on, so now I'm getting all the prickles and everything like that. And yes, that's why you're never going to see me again until May 25th, when the barbers open again. Talk about a bad idea. Now, 2 pi times that times 2.38. Divided by, and of course now we know the natural log is 1.92, so I'll just write it down there, all right, because you already know it. And if we run through that whole thing and we multiply that all out, what we end up getting is 68 picofarads per meter, right, for the 75 ohm coaxial cable that you have. All right, now to figure out what R prime is, we have to figure out what R sub S is first, right? So let's do that. And so far up to now, we really haven't had to name the frequency at which we're working here, but here's what I want to do. I want to put this at the very high end of what a coax can handle. A coax can handle about 600 megahertz. So I'm going to say that our frequency for this example is 500 megahertz. And later on, what I'm going to do is I'm going to compare that 500 megahertz to a 500 hertz waveform that travels down the same coaxial cable. And I want you to see the difference in the attenuation per kilometer that you know, has. So anyway, we're still doing a lot of this. So let's get back to this. So I've got pi, right, times my frequency, which is 500 megahertz. I'll let you put the times 10 to the 6th in there, times 4 pi times 10 to the minus 7 henries per meter, times 16 times 10 to the minus 9 ohm meters, all taken. Just a second, okay? Just a second. Okay, I'm back. No, I thought somebody knocked at the door, but they didn't. So that is okay then. So anyway, if I do take the square root of that, I should get 5.6 times 10 to the minus 3 ohms, right? And it is ohms because remember we've got meters in the bottom here, so we're going to get that later. So let me get R prime. I hope that I did that right. Yes. Okay. So this is going to be now. This is for copper, by the way. So I'm going to put that disclaimer here, equals a copper electrode. And of course, that would be pretty much correct because that's what the electrode is. Well, in any in any good new coaxial cable. The older coaxial cables, by the way, you'll find that they have aluminum center conductors. Those didn't work because they oxidize up. And so now most of the ones that you see are copper center conductors with aluminum outside braided shield. Let's get back to this now. So if I have 5.6 times 10 to the minus 3 ohms, ohms, divided by 2 pi times 1 divided by 0.001 meter. Remember, we got to work in meters here. 1 divided by 0.00682 meters, right? And that gives me an R prime of 1.03. I hope to God that's right. Yeah. 1.03 ohms per meter. Not too bad, 1.03 ohms per meter. You think, hey, that's pretty good, right? So now we have all, I'll try to find the red marker. So now we have all of our things here. I'm just going to circle them. So we've got R sub S is here, right? We needed R sub S so that we could get R prime. And we've got C prime now. And we've got L prime for this configuration of the 75 ohm coaxial cable. We also know, what the center radius is. We know what the outer radius of the ground shield is going to be. We know, well, I think, let's see, we've got everything else there, characteristic impedance and everything. So I'm going to end that there. I don't know how long. I forgot to time myself. I'll try to look at for the red thing. And then I want to continue on from here, because what I want to do now is I want to take all of these individual numbers and put them into our propagation constant equation, which is a complex constant. And then we can see how the attenuation and phase shift modifications are going to occur down the line for the transmission line. All right. So I'll end it there, and I'll try. I want to get another lecture in today, so to finish this up. And then what we want to do is we want to look at other geometries, not just coaxial cables. We want to look at microstrip transmission lines on the printed circuit board in your cell phone. And we want to look at twin lead transmission lines, which when I say twin lead transmission lines, I not only need small little twin lead transmission lines like we're on your parents' antenna or what you might see on your FM tuner. I'm also talking about larger two-wire transmission lines, right? So we want to look at those, and those have different geometries, and therefore they require different equations. But they don't require different equations when you're then solving for the propagation constant. So that's what we want to look at next. Okay, see you later.